All right, so we're going to continue looking at vectors. And the first thing I want to look at is what does it mean for two vectors to be equal to each other? All right, so I'm going to draw a picture, and I want you to tell me if you think the two vectors are equal. Let's go like this. Okay, let's do this on a grid. That's fine. So I'm going to draw this vector like that, and then I'm going to do one over here like that. Okay. So what do we think? We think those two vectors are equal to each other. Nick, what do you think?
Yeah, because they go to the right before up.
Right. It doesn't matter if they start and end at the same points. They both have different initial and different terminal points. What it means for two vectors to be equal is that if you compare the horizontal components to each other, those are the same. So if we look at that, they're both 2 to the right. And then if you compare the vertical components, okay, y1 and y2, they have to be the same. 4 up, 4 up. So those are the same vector, even though they do not have the same initial and the terminal point. Okay. All right, so the last way we're going to look at writing two vectors, writing vectors without drawing them, is called unit vector notation. This is the notation that's probably the one we're going to use the most when we want to write vectors without drawing them. So one notation we have already is with the angle brackets, kind of like the less than and the greater than sign. Two numbers in the middle with a comma. But this way is going to use what's called unit vectors. What does it mean again if a vector is a unit vector? Lens? It has a what of one? Anybody give me the word we used yesterday? Yeah.
Magnitude.
Magnitude. Yeah. So it has a magnitude of 1. So we're going to look at two special vectors that have magnitudes of 1. Okay. The first vector is I. So when we're talking about vectors, I is a special name. We can't use I when we want to name one of our vectors, okay, because I means something special. And I is always a vector that is 1 unit long and points to the right. Always. So that's always what I has to be. 1 unit long and it points to the right. Okay. I looks just like that. Another unit vector that, again, it's going to have a special name, and we can't use this letter to name any of our vectors, is J. So J is a vector 1 unit long, and it points up. So if you want to name your vector that you're working with, unless it's exactly 1 unit long and pointing right, or 1 unit long and pointing up, don't use an I and a J. And J looks like that. 1 unit long, and it points up. And to work in 2D, that's all that we're going to need. Yes? Yeah, just. Okay. If we're going to work in 3D, we would need one more unit vector, but this time we don't. Okay. Anybody have a guess what the third one would be called? Anyone have a guess what the third unit vector would be called when we get to 3D? Yeah? K. Yep. So we're going to use K. But we'll wait till Thursday before we talk about that. So the idea is we're going to take I's and J's and we're going to put them together to kind of build whatever vector we want to build. Okay, so we're going to stack. I think of these as like pieces we can stack together. let's take a look at how we would build the vector 3, 4 out of i's and j's. And once we build it, then I think you'll see kind of how the notation works. All right. So we want to build the vector 3, 4. What's the horizontal component of the vector 3, 4? Yeah, 3. Okay, so we're going to start with that. We need to build something that has a horizontal length of 3. So for that, we're going to use our i's. And how many of the i's would we need to stack together to build something that's 3 units long? Yeah.
3 i's.
Yeah, we're going to need 3 of the i's. So I'm going to just draw them over here. There's 1, 2, 3. And how would we name that vector in green, you think? Yeah?
3i.
3i, yeah. So that is 3i plus, now we need to build something on there that has a vertical length. And what's the vertical component of our vector? Travis. And what's the length of our vertical component?
4j.
4, yep, we're going to need 4 of them. Okay, so we know it's a 4 from right there. So we're going to take 1j, 2, 3, 4. Okay, so now we've built kind of like 2 sides of a triangle, and the height is now 4 of the j's stacked together. So what do you think we're going to call that vector in blue? Yeah, 4j. So now, to write our final answer, this is kind of what we did yesterday with the visual part. We would draw from where we started to where we finish. And that vector in black is the vector 3, 4, because it goes right 3 and up 4. So yesterday we wrote it like that. Today, we're writing it like that. So that is the vector 3i plus 4j. And this is called unit vector notation. So now, we can build any vector we want that goes up and to the right. But what if we wanted to build, say, a vector like that? What would we have to do to build something, because that goes in a different direction? Yeah. Yeah, we could use negatives, right? So that might be negative 1i plus maybe 2.5 or 3j, somewhere around there. Okay? So it's a negative I and then stacking up the j's. So by making these positives and negatives, we can go in any direction that we need to build any vector that we want. And we can also use parts of I and j. So if you had to build a vector, you know, something like this, you could say that that's 3i plus 1.5j. Right? So you could do things like that too. And so, any question on this idea of unit vector notation? Okay, remember, when I write it, okay, the I and the j, those are bold. Okay? These are like scalar products. That's from what we did yesterday. 3i plus 4j. So now we're going to look at everything that we did pretty much yesterday, but we're going to do it again without any sketching. Okay, so I'm going to give you 2 vectors. Okay, I'm going to call the vectors v and w. Alpha is going to represent a scalar. And we're going to look at how we add, subtract, and scale without any sketches. Here's our 2 vectors. Now, I'm going to switch between both notations, the one that we did yesterday and the unit vector that I just showed you. Because you might see both in the homework and on the test. So each vector that we're going to work with has a horizontal and a vertical component. The first step is adding two vectors together. Okay, doing it visually, that's where you take one vector, you position the other one, and so it starts at the end of the first one, and then you draw in your diagonal. If we want to just do it numerically, all we have to do is add like components together. So take the horizontal from the first vector, take the horizontal from the second vector, add them together, and that's going to be the new horizontal in the final vector. Okay, same for the verticals. Take the vertical from the first, vertical from the second, add them together, and that's going to be the new vertical of the composite vector, v plus w. How about, Dario, how do you think we do subtraction?
Would it just be, just put the sides?
So what do you think, what would be the formula for the horizontal component of v minus w? X1 minus x2. Okay, so when we did subtraction before, we had to take the second vector, we had to flip it around, and then add it to the first. Okay, that's great for a visual, but we're not doing a visual. Okay, we're just doing it numerically. Okay, and Ethan, how about the formula for the vertical component of v minus w? y1 minus y2. Would it make a difference if I did y2 minus y1? Yes, right? Because subtraction is not commutative. So when you are doing subtraction, make sure you follow the order that they give you. The component from v comes first, component from w came second. With addition, no, it doesn't matter. We saw that yesterday. Okay, what do we call this? When we put something like that in front of a vector? Yep, scalar. That's a scalar, right? So this is a scalar product. To do a scalar product, think of the scalar as being distributed to each component. You're going to distribute it to the horizontal and to the vertical. Right? When you're doing a scalar product by itself, you don't need two vectors. When you're adding and subtracting, you do. You can't add and subtract unless you have two things to work with. All right, and the last one. What does that symbol mean when we put a vector and then put those double bars around it? That's,
Would it just be the magnitude?
that means it's magnitude, yep. And kind of drew an example today, and I think we talked about it yesterday. How are we going to find the magnitude of a vector? Anybody remember what formula I said we were going to use? Yep. Yep, we're going to use Pythagorean theorem. There's a perfect picture right there. If you want to find the length of the vector 3, 4, you've got the base is 3, the height is 4, use Pythagorean theorem, and you would get the length of the vector 3, 4 to come out to how much? 5. Yep. That would be the length of the vector. So it's the horizontal component squared, vertical component squared, add them together, and then take the square root. And magnitude is another example of a calculation you can do with a single vector. You don't need two vectors to find the magnitude, just one vector. And out of the 4 operations we just did, add, subtract, scale, and magnitude, which one has an answer, a type, that's different from all the others? Yeah.
Magnitude.
The magnitude, yeah. Magnitude is a different answer type. All the other answer types are vectors. But when you find magnitude, you don't write your answer as a vector. You just write it as a number. And what did we say for magnitude? It's always going to be what kind of number? It's always going to be a positive number. Yep. Okay. So let's try some examples. I've given you two vectors in both notations, unit vector, algebraic vector. And we're going to add, subtract, scale, and do a magnitude. Do one of each. Okay, so let's try adding. And first, let's do it. Let's do it where we do the unit vector notation first, and then we'll write it in the other notation we learned yesterday after. Okay, so remember adding, combine the horizontal components, and then combine your vertical components. Okay. Anyone think they could tell me what v plus w would be in the unit vector notation? Yeah.
5i minus 1j.
Yep. So 5i, you can put minus 1j, or you can just put minus j. That's fine too. So it's 5i minus j. And then how about if we wrote that in the notation we learned yesterday from Greg?
5 minus 1.
Yep. So we need a 5 and a negative 1. Don't mix the two notations. All right. If you accidentally put i's and j's in with the angle brackets, that's wrong. Or if you put angle brackets around the i's and j's, you got to pick one format or the other. You can't mix them. Let's try v minus w. All right. So, Marin, could you tell me what v minus w would be? And let's do it first as a unit vector.
Negative 1i plus, negative 1i plus 7.
Negative
Okay.
1i plus what?
7.
7j. Yep. So I'm just going to do negative I. So that's 2 minus 3. And then the j is 3 minus negative 4. So plus 7j. Right. And how about, Annalise, if I wrote that in the other notation, what would we have there?
Negative 1, 7.
Negative 1, 7. Perfect. Okay. So what we just did there takes the place of drawing out the vectors and having to figure it out that way. Let's try C. So that's a scalar product. So we're finding 3v. Nick, what would 3v be? What would 3v come out to as a unit vector?
6i plus 9j.
6i plus 9j. And there it is in our other notation as well. Okay, so again, those three all have the same kind of answer. They all have vectors. The last one we're going to do not write your answer as a vector, because it's not. It's a number. So Travis, could you tell me the calculation that I have to set up to find the magnitude of v?
The square root of 2 squared plus 3 squared.
Good. So the square root of 2 squared plus 3 squared. That's going to give me the square root of 4 plus 9. If they're looking for an exact answer, we'll just leave it like that. Okay, so any questions on adding, subtracting, scaling, or finding magnitude? So just a reminder, we kind of already went over this, but if we have a vector that has a magnitude of 1, it's called a unit vector. So let's pretend like that red one is a unit vector. The black one points in the same direction as the red one, but it's not a unit vector. It's too long. So what can we do to a vector to change its length? What did we say yesterday? I'm looking for the word we could, proper word for changing the length. scale it. Yeah, we're going to scale it. So what I want to look at is if we have a vector that's not a unit vector, I would like a formula that can convert it into a unit vector. I don't want the formula to do anything to the direction. I want it to keep that exactly the same. But I want to make sure that the length comes out to 1. Anybody think they know what you can scale a vector by, for kind of like a formula, that will force the length to always be 1? Yeah?
Like the reciprocal?
The reciprocal of what?
The reciprocal of like the length.
Yeah, the reciprocal of the length. So for example, if you had a vector that was 5 units long, and you wanted to force that to be 1 unit long, then you would scale by 1/5. If you had a vector that was 1/3 of a unit long, and you wanted to force it to be 1 unit, you would scale it by 3. Because if you scale something 3 times as big and it's 1/3 of a unit, it would turn into 1 unit. So then if you have something that is x units long, you would scale it by 1/x. So the idea is you scale it by the reciprocal of its magnitude. And if it already was a unit vector, then scaling it by the reciprocal of the magnitude won't change it. It will stay as a unit vector. Okay. All right, so let's write that down. So what we're doing is we're finding a new vector, points exactly the same way as the old one, but if it wasn't 1 unit long, it will be now. Okay. So I'm going to use the letter U to represent a unit vector. And let's say we had the vector V. Okay, we don't know if the vector V is a unit vector right now. It's just a vector. But if we want to transform it into a unit vector, then we can take vector V and scale it by 1 over its magnitude. So scale the vector by 1 over its magnitude. And if you want to put all that together, you can. You could write it by multiplying this out, which would be V over its magnitude. And that is how you can find a unit vector. So remember, with that scalar in front, it's like we're going to distribute the scalar to each component of our vector. All right, so let's see, before we do our word problems, we're going to look at this example. We'll do one of them, and then that I think will be the last new thing for today. And then the word problems, they're just going to use things we've already learned. Probably a lot of trig, but nothing new. Okay, so let's find the unit vector for 3i minus 4j. And in general, when they give you a problem on the test, they're going to give you one format or the other. So whatever format they give you for the vector, just give back that format in the answer. Okay. What's the first thing that we have to do to figure out if we already have a unit vector? What do we have to figure out first? Yep.
Find the magnitude.
Yeah, find the magnitude. Maybe we already have a unit vector and we're done. If not, then we'll use the formula. What would be the magnitude of V in this case? Yep, 5. Okay. 3, 4, 5. It's a 3, 4, 5 right triangle. Okay, so we don't have a unit vector. Okay, the magnitude is 5. So what would I have to scale vector V by to turn it into a unit vector without changing its length? I mean, yeah, without changing its direction. 1/5. Okay. So what would be our new vector if we scale V by 1/5? And let's write the answer in unit vector form. Yep.
3/5 I minus 4/5 J.
Yep, exactly. 3/5 I minus 4/5 J. And now if you did Pythagorean theorem on that and checked it, you would get 9/25 plus 16/25. That's 25/25. And then if you take the square root of 25 over 25, you get 1. So yeah, we found a vector that was a little bit shorter, 5 times as short, but it's now a unit vector. Any question how we did that? Okay. So I told you when we started looking at vectors, we had two main types of examples. Velocity was one, force was another. We're going to do, I think we're going to get to one of each today. So the first example we're going to look at is velocity. I think the velocity one is a little bit easier. It requires some trig, but as long as we know the trig, that won't be too bad. But there's less background information you need to know to do this. The force problem, you have to understand a little bit of very basic ideas in physics, but if you haven't had physics, that's okay, we'll look at it. Okay, so let's start with a velocity vector. So when I give you a problem about velocity, I'm not going to give you the velocity vector. I'm going to give you information like this. I will tell you an angle that an object is being thrown at and a speed. Now, when we write a vector, is there any spot in a vector for an angle? Do we ever use an angle when we're writing vectors? Jackson?
No.
No. We write components, horizontal and vertical. So to figure out a velocity vector, you're going to have to translate angles and magnitudes into horizontal and vertical components. So let's see how we can do that. So when we do a velocity vector, technically the object would not keep traveling in a straight line. If there was gravity, it would start to curve back down. But for our purpose, we're just going to assume the object just keeps going straight. So we'll pretend like it's not influenced by gravity. Okay, so maybe outer space. So the angle that I give you is going to be right there. The angle is generally going to be the angle with the ground. Right? That's called an angle of elevation. Okay, think of like if you had a target you're trying to aim like a laser at up above you. The angle you would have to tilt that laser at to be pointed at the target, that's the angle of elevation. All right, so we've got to break a vector down into its components. So what do you think I'm going to draw in that picture to start to figure out the components? Yeah. We are going to draw more vectors, and that's going to create a certain shape. Yep.
Right triangle.
Yeah, we're going to make a right triangle. Okay, so to make a right triangle, I need a straight edge just to make a vertical. Let's put our vertical over here. And now I can break that vector in black down into two vectors. Think of that vector in black. That's the actual path that the object is going to travel. But we need the components of the path that it's going to travel. That's how you write a vector. So this is the horizontal component of the path it travels. And this is the vertical. Let's call the horizontal component the x. And we'll call the vertical component the y. Let's start with coming up with a formula for the horizontal component. You're going to know theta, and you're going to know the magnitude of v, because the magnitude is going to be the length of that arrow, and that's going to represent the speed of the object. So how do you think we could write down a formula that would involve the magnitude of v, theta, and x? we use to do that? Yeah.
Use cosine.
Yep, we use cosine. And what would your formula be? Cosine theta, yep. X over what? Well, if I do x over v, then it would actually be that. That's v. It's a picture. Do I want the picture of v in the denominator of my fraction? No, not the picture. What about v do I want in the denominator?
Did you just want the speed?
Yes. So how would I write that? Travis?
Would it be x over the magnitude?
X over the magnitude of the vector. Yep. That's your formula. And the magnitude is the speed that the object is being thrown. So now what we need is a formula for x, because when we're done, we're going to put something here and something here. We're going to figure out what goes right here. That's what we're doing first. What would x be when you solve for it in that equation? Yeah. Yeah. So I'm going to just put the magnitude in front so there's no confusion about it, whether it's part of the argument or not. So x is the magnitude of v cosine theta, and that would go right there. And doing a very similar setup, what do you think the formula would be for the vertical component of your vector, given the angle of the object and the speed of the object? Yeah. Right, magnitude of v, sine theta. That is the formula for a velocity vector. I'll write that down a little nicely on the next page, but those are going to be our those are the formulas for the two components. Okay. A number times cosine will always give you a horizontal component. A number times sine always gives you a vertical component. Let's write this down. So magnitude cosine and magnitude sine. If you want to write it with the unit vector, i's and j's, we can do that too. I had used a different Greek letter, but that's just a placeholder. So when you write it with the unit vector, you could actually factor out the v, or you could leave it distributed. If you leave it distributed, it would look like this. Magnitude v, cosine theta I, that would be a bold I, plus magnitude v, sine theta j. Okay, so same thing. I'm just showing you the algebraic vector notation and unit vector notation. And make sure we remember what those two things are. Theta is the angle that the object is being thrown at, and v is the initial velocity. Now that would be the initial velocity if the object was being thrown at you. So if you were standing right here and you pointed a radar gun like that at the object, you would detect it coming at you at 50 miles per hour. So the beam of your radar gun would have to be in line with the path the object is traveling. So now let's see if we can work through that word problem that I showed a few minutes ago where I give you the angle, the speed, and you break that down into its components and give me the vector. Okay, so we have an object being thrown 50 miles per hour at an angle of 30 degrees. So again, that means if you were lined up with the object and you pointed the radar gun towards the object at 30 degrees, it would read 50 miles an hour. Okay, that speed only works if you're lined up with the object. That's why you'd never see, like, if a police car was measuring speed, they wouldn't be able to do it really that accurately if they were like up on a cliff and you were down on the road, because they wouldn't be lined up with you. Okay, they generally try to do it where you're at the same elevation. So you're on a road, they're on a road, and it's flat. Even though they're generally not right in front of your car when they get the speed, the radar gun can calculate and figure out that angle. Because remember, you're not driving straight at the car. You're coming at the car kind of at an angle because it's on the side and you're coming this way. And technically, if they tried to get the speed when you were right lined up with them, it would probably say 0, because they'd be pointing a radar gun at like your passenger side door at that point, and you're not coming at the car anymore. So it figures out that angle as it's moving. So it does use some trait to figure it out. Right. So let's start with our components. What's going to be the formula for my number that's going to go in front of I? Lens?
Median magnitude V cosine theta.
Yep. And can you fill in what we have for our problem?
So it would be 50 cosine 30.
So we got 50 cosine 30. We'll do that out. That's what goes in front of I. And then what about the part that's going to go in front of J? Yep. 50 sine 30. Right. So let's see what happens when we type those in. So we've got 50 cosine 30. 50 cosine 30. That's going to give us 43.3 I. Plus, and what's the sine of 30? Think about on the unit circle. 30 degrees is right here. Yeah, 1/2. It's the short side in a 30, 60, 90. The long side is root 3 over 2. I can't really multiply root 3 over 2 in my head times 50. But this one we should be able to. 1/2 times 50 gives us 25J. So that is the velocity vector for the problem. So now it says to explain the meaning of each component. So what does the 43.3 mean in this problem?
It's the horizontal distance the object's going.
What do you mean the horizontal? Well, we don't. So you're saying it's going to travel 43 feet and then like stop?
Maybe the initial. How far would like initially go?
So the 43.3 is not a measure of distance. When you find components of a velocity vector, there's not a, those numbers don't directly represent a distance. Anyone else have an idea what the 43.3 is? What?
Could it just be,
What is that?
could it just be the x component
Of what?
of the velocity?
Okay. So explain to me what that means in like real life in this problem.
Oh, like in real, like in real life, you travel 43.3 meters horizontally,
You're traveling 43.3 what?
43.3 miles.
So you're saying it's a distance?
It's not a distance.
It's not a distance. No. It's not a distance. Yep.
Isn't it a speed?
It is a speed. What kind of speed?
Like the speed of it going, right?
Yes, it's a horizontal speed of the object. So basically you could imagine if, let's say this object could travel forever, right? And you were driving on a road and you drove at 43.3 miles per hour straight on the road, and this object was traveling at 50 miles per hour at an angle of 30 degrees. If you both started at the same time, you would be under the object the whole time. Right? If you drove 50, you'd be going faster, right? Because that 50 miles per hour isn't all in the horizontal direction. Part of it's in a vertical direction. So if you wanted to keep up and stay right under the object as it traveled, you would go 43.3 miles per hour, and you'd stay right underneath it. Right? The 25 miles or per hour, or whatever, was it miles? Yeah, miles per hour. That's the vertical speed. So if you wanted to, let's say you were in a helicopter and you wanted to stay next to it the whole time as it went up, the helicopter would have to be going up at 25 miles per hour, straight up. And as long as it was doing that, you would stay next to this object as it traveled the whole time. You'd be at the same height of the object. Any question on that? So it's the components of the speed, the horizontal and the vertical speed. All right, so that's the velocity vector problem. And the last one we're going to look at is the force problem. So this particular problem we're going to look at has to do with what's called static equilibrium. What does it mean, physics meaning, of the word static? Yeah? Not moving. Static is the opposite of dynamic. Right? Dynamic means things are moving. Static means it's not moving. Equilibrium means everything is balanced. Right? Everything's equal. So we're looking at a problem where all the forces acting on our object are balanced and nothing in the problem is going to be moving. Everything is stationary. And the only way that an object cannot be moving is if whatever forces are acting on it are equal on all sides. So for our purposes, we're going to be looking at a two-dimensional problem. So we have forces horizontally and we have forces vertically. Okay, that's how we'll break down our forces. So what I want to do is find the amount of tension that's going to be in two different cables supporting an object. Now, if you hang, let's say, like 1,000 pounds of weight from two cables, would there always be 500 pounds of tension in each cable? What do you think? Yeah?
Could we split between the two cables?
So you think the tension would be exactly equal
Yeah.
in the two cables? It would only be equal if the cables were positioned how? Yep.
The angle is the same.
If the angle was, yeah, the same, right? So assuming the weight was uniformly distributed on the object you were supporting as well. But yeah, the tension would only be equal if the cables supporting them were at the same angle. Now, in our problem, the cables are not going to be at the same angle, so the tension in each cable is not going to be equal. Right? Now, does the tension in the cables have to equal the weight of the object that it's supporting? What do you think? Will the tension in the cables always equal the weight that it's supporting? What?
Probably in order to keep the weight from falling down, yes.
So let's say you had a tug of war rope, and the rope weighed 50 pounds. And I put, 50 people on, each side pulling. Do you think that there could be more tension in the rope than it actually weighs? Yeah. So the tension in the rope is partially controlled by the weight, but it's also controlled by the angles. Think about how hard you would have to pull if you were trying to support 1,200 pounds, but you weren't pulling straight up on it. You were pulling sideways on it to try to get it to hang in a certain spot. You would have to pull a lot harder at an angle of 30 degrees than you'd have to pull if you were pulling at 9, like straight up on it. Right? So you could have more tension in these cables added together than 1,200. Definitely could have more, right? Because the two cables they're at angles. They're not straight. They're not perpendicular. All right, so the object is not moving. So first thing we want to do is kind of write down some basic ideas. We're not even going to do anything with numbers and angles yet. Just more concepts. What are the two directions that this object could move in if we're assuming it's like a two-dimensional world? What are our directions of movement that could happen? Mervyn, what do you think? So what are our two directions that we could move in? So thinking about like this is a two-dimensional space, and I'm trying to get towards like the components of vectors. So I'm thinking we have two different directions that this object could move in.
So it would just be the way that it's facing. Can you feel that way or that way?
Let me describe it a different way. Let's think of it as like axes of motion. What are the different axes that this object could move along?
Oh, the X or the Y.
Right, it could move either in a horizontal direction or a vertical direction or some combination of the two. But we could break down the movement of this object if the cables were to fall or come apart into horizontal movement and vertical movement. Well, this object isn't moving. So what does that mean about the horizontal forces acting on it if it's not moving? Yep, they're balanced. So what are the two directions that we have for horizontal forces? We have a force that could pull it which way? Yep, to the left and to the right. But it's not moving left and right. So then that means that the force that's pulling it to the left must be equal to the force that's pulling it to the right. If they weren't equal, then it would be swinging. Okay, and it's not. Okay. What else must be equal here besides those two forces? Yep.
The force one. All of the force one.
Right, the force up and the force down. So the force up has to equal the force down. Okay, that's very conceptual. It's abstract. It's not very specific with the numbers in our problem yet, but it does represent what's going on. So now we've got to kind of build these equations out, but we've got to use the numbers in our problem, and we have to start thinking about our forces as left, right, up, and down. So right now, the tension in this cable is pulling really two directions. Let's call this the tension in cable 1 and tension in cable 2. Which way is cable 1 pulling on the object? So think about what would happen if you cut cable 1. What would happen to the weight? Yeah.
Cable 1's pulling it left.
All right, it's pulling it left, and what else?
Holding it up.
Up. Cable 1 is pulling left and up, because if you cut cable 1, that weight would drop a little bit, and it would swing to the right. So it would go down and towards the right. So this cable must be pulling up and to the left, and this one is pulling up and to the right. Okay? Because if you cut cable 2, it would swing left and it would drop down. All right. So now what we have to do is we have to start breaking down the tensions into their components. And what are we going to draw to break the tensions into their components? Yeah, right triangles. We're going to draw right triangles. Bunch of right triangles. Right, so we're going to have a horizontal here, and we're going to need a couple verticals. Let's put a vertical here, and another vertical there. So this is kind of like the velocity problem now. I'm going to break down each tension into a horizontal and a vertical component. So I've got a horizontal component from cable 1 that I can represent like that. And I've got a horizontal component in cable 2 that I can represent like that. I got a vertical component in cable 1 that can be represented that way. And I got a vertical component in cable 2 that can be represented that way. Now, to be able to start to put those into the equation, we need to name all of them. So let's name all the horizontals x's and all the verticals y. And we'll use the 1 and the 2 subscripts. Okay, so this would be x1, x2, y1, y2. So now I want to start to translate left, right, up, and down into the vectors in that picture. Okay, let's start with force left. What are we going to substitute in for the force that's pulling left? Yep, x1. Okay, so this is like the second stage of our equations now. It's getting a little more specific to our problem and less abstract. So x1 has to equal, what's the force pulling to the right? Yep, x2. Okay, we still haven't put in the angles, the 30s and the 45s and all that. We still have to do that, and that's going to involve breaking things down with trig, but we'll get to that. Now the force up. What's the force pulling up in this one? Yeah.
Y1 and Y2.
Y1 and Y2, and they're working together, because if either cable was cut, the weight wouldn't fall all the way, because both cables are working together to hold it up. So Y1 plus Y2, that's the force pulling up. What's the force down? Yep. well, T1 and T2, those are on angles, so we're not going to actually be using those for this part. We will use them in a little bit, but they don't pull down. Yeah, the 1,200 pounds, that's the force pulling down. Okay, so there's the second stage of your equations. Now we got to get rid of all those x1s, y1s, x2s. We need to start substituting in angles from our problem. Okay, right now we don't have any angles inside the triangles. We really need to get angles inside. How much is this angle in the lower right of the triangle with all the ones on it? Yeah.
Would be 20 degrees.
This angle? Nope, it's not 20. Yeah, 30. Yeah, this angle's 30 because we have two parallel lines and we have a transversal going across them, so those alternate interior angles would be the same. There's other ways you can think about it as well. How about this angle on the other side of the 30 over in the second triangle? How much is that one? Yep. 45. Okay, so now let's see if we can come up with formulas for x1, x2, y1, and y2 using our angles and the other labels in the triangle. Let's start with x1. What trig function would you use that would involve x1, the angle, and the tension? Yeah. Yep, any horizontal force is always going to use a cosine. Verticals are always going to use sine, just like velocity. So cosine of your angle equals adjacent over hypotenuse. And the hypotenuse is T1. It stands for tension in cable 1. Now solve for x1. T1 cosine 30. That is your formula for x1. How about x2? Anyone think they could tell me what the formula for x2 will be? Yep.
T2 cosine 45.
Good. T2 cosine 45. Okay, now let's do y1 and y2. How about the formula for y1? Yep.
T1 sine 30.
Yep, T1 sine 30. And the formula for y2. Let's
T2 sine 45.
T2 sine 45. Okay, so we just finished the trig part of this problem. Okay, the trig is done. Now it's all out. Substitution and solving systems of equations. We've got to substitute in everything we have for x1 and x2. So let's do that. So we have T1 cosine 30 equals T2 cosine 45. And we're trying to solve for the tension in cables 1 and 2. The problem with that is there's two variables in the same equation, so we can't get an answer from that. But that's okay because we have a second equation. Right? So we have two variables, we have two equations, we're just solving a system. So y1 is T1 sine 30. Oops. Plus y2 is T2 sine 45. And that is your system of equations you need to solve. Okay, what's one method that we can use to solve a system? Yeah. We can use elimination. That usually works well when you have integer numbers and we can multiply to make something cancel. We've got really messy numbers here, so elimination could be a little hard to do. What's another method? Yep. Substitution. Which equation here do you think it's easier to get one of the t's by itself, the top or the bottom? Yeah, I would say the top. You can get either t1 or t2 by itself in one step. Let's do t1. T1 would be t2 cosine 45. And then I would divide by cosine 30. Okay. So there's my formula for t1. And what am I going to do with this? Yeah. Yeah. We're going to substitute it in for t1 right there. So the first tension we are solving for is the tension in cable 2, just the way we did it. All right, so we've got T2 cosine 45 over cosine 30 times the sine of 30 plus T2 sine 45 equals 1200. Now it's just a matter, we got to get some decimals and do all this out. So I'm going to multiply cosine 45 times sine 30 and then divide by cosine 30. Okay, and we'll round to, well, let's see what our answer looks like. Cosine 45. Let's multiply by sine 30. And then I'll divide by cosine 30. Let's say 0.408. 0.408 T2 plus the sine of 45, that's 0.707. I know that one because sine 45, it comes from 4590 right triangle. Okay, so we'll combine like terms. We've got 0.408 plus 0.707 gives us 1.115. And what's our last step? Yeah. Yep, and how would you do that? Yep, divide by 1.115. Okay, so the tension in cable 2 is 1,076. Just say 23. And I think our book measures it in pounds. I technically don't know if you're supposed to measure force in pounds. It's really newtons per lib. We're not going to get into that. So I'm just looking for the number. So there's the tension in cable 2. And now use this to find the tension in cable 1. It's the tension times the cosine of 45 divided by the cosine of 30. So let's just take the answer we have right there, multiply by cosine 45, and divide by cosine of 30. So we get a tension in cable 2 of 878.7, or tension 1, sorry. Tension in 1 is 878.74. So you can see that if you add the two together, it is definitely more than 1,200 total pounds of tension. Okay, but that's pretty much the steps, as organized as I can make it, to solve a problem like that. Okay, and if once you do enough of them, you can kind of start to maybe skip that first step of force left equals force right, and you can really go right to your diagram, because as long as it's always two cables, these equations are going to stay exactly the same every time. All you have to do is change the 30 and the 45 to whatever the two angles are at the bottom. And really, you can go right to that step in blue if you keep that template as how to do the whole problem. We don't have to work through every time to figure that out. Yeah.
How did you get to T1?
T1. So I just plugged into the formula right here that says T1 equals. Yep. Multiply by the cosine 45 and divide by cosine 30. Okay, so that is 8.5 parking. There is one question I just need to change. Okay. So 25 to 47, those are the odds. And then 55, 57, 64, and 66. Actually, no, just 66. So that's the homework for tonight.